Welcome to Night Cosmos Sleep, farther from Earth than any human-made machine has ever traveled. Voyager 1 is still quietly sending signals home, but after nearly half a century, its power is slowly fading, and each instrument that is switched off may be a part of the spacecraft that will never awaken again. NASA is trying to keep Voyager alive one day at a time, but no one knows which signal will be the last. The story begins when a command is sent into the darkness, and Earth must wait nearly 2 days to learn whether the spacecraft will answer. An engineer on Earth presses the button to send the command. No unusual sound fills the room, and no large warning light flashes as it might in a movie about space. There is only a radio signal leaving an antenna on the ground, beginning its long journey through the darkness between the planets. Its destination is Voyager 1, a spacecraft now about 25 billion kilometers from humanity. The distance is so vast that even light, the fastest thing known to us, takes nearly 23 hours to cross it in one direction. The command cannot reach Voyager immediately. It must continue traveling through space for almost an entire day. During that time, the people on Earth have no way of knowing exactly what is happening aboard the spacecraft. They can only watch the quiet screens in front of them and wait for the signal to complete its journey. No one can call it back and correct the command if a detail turns out to be wrong. No one can ask Voyager whether it understood the request correctly, and no one can directly observe the components operating on the far side of that immense distance. When the signal finally arrives, Voyager 1 must carry out each step on its own, following instructions prepared in advance. Then the spacecraft's reply needs another 23 hours to return, turning even a simple exchange into a process that can last nearly 2 days. This command does not ask Voyager to change course or begin a new observation. It asks the spacecraft to shut down an instrument that has traveled with it for almost half a century. That instrument is called the Low Energy Charged Particle Instrument, more commonly known as LECP. For decades, LECP has monitored charged particles and high-energy particles moving through the environment around Voyager. These particles are far too small for the human eye to see, but their presence helps scientists understand what kind of space the spacecraft is passing through. LECP was operating when Voyager 1 flew past Jupiter and Saturn, through regions of powerful magnetic fields and intense streams of particles surrounding the two giant planets. It continued working as Voyager moved away from those worlds, crossed the outer reaches of the Sun's influence, and entered interstellar space. Nearly 49 years after leaving Earth, the instrument was still sending data home. But by 2026, scientific value was no longer the only thing that had to be considered. Voyager 1 was running low on power, and the energy that remained was no longer enough to support everything that had once operated aboard the spacecraft. Voyager's power supply did not disappear suddenly in a single night. It declined slowly, year after year. It was like the flame in an old lamp, growing smaller after too many winters, not yet extinguished, but no longer bright enough to illuminate every room. The remaining electricity had to be divided among the communication system, computers, scientific instruments, and the components that needed to stay warm enough to keep functioning. For years, the mission team had searched for ways to save every possible fraction of power. Some instruments were switched off after their work had ended, while many heaters no longer received the energy they once had. Systems that had once operated together now had to take turns, yielding the spacecraft's limited power to one another. By early 2026, Voyager 1's electrical margin had grown even smaller. After an adjustment on February 27th, the spacecraft's power level fell more than expected. The change did not cause Voyager to stop working immediately, but it shortened the time available for careful consideration. The engineering team no longer had much of a safety margin in which to delay a difficult decision. If the voltage dropped below a certain limit, Voyager could automatically enter a protective state. In that condition, the spacecraft would prioritize the basic functions needed to survive, while scientific operations might be suspended. This was not something the mission team wanted the spacecraft to do unexpectedly. From almost a light day away, Returning a system from a protective state to normal operation could take many days, with no guarantee of success. The engineers therefore had to choose between two things that both mattered. They could keep LECP operating and continue receiving data from the interstellar environment, but the power used by the instrument would reduce the safety margin of the entire spacecraft. Or they could shut LECP down, accepting the loss of part of Voyager's ability to observe its surroundings in exchange for more time to preserve communications and protect the systems that remained. This was not a choice between a useful instrument and one that no longer mattered. It was a choice between science in the present and the future lifetime of the mission. Keeping LECP active meant continuing to receive measurements that no other spacecraft could provide from the same location. Turning it off meant closing down a sense that had been working since the earliest days of the journey. Yet without shutting the instrument down, Voyager could move closer to the point where the entire spacecraft no longer had enough power to operate reliably. In the end, the mission team had to protect the spacecraft before it could protect every individual instrument inside it. Voyager can be imagined as a very old house in the middle of a winter that never ends. The power flowing into the house weakens year by year, while the people inside have no way to replace the wiring, install a new generator, or call someone to make repairs. At first, they turn off the rooms they no longer use. Then they dim the lights and keep only the communications system and the spaces that must remain warm. Eventually, they find themselves standing before a room that is still useful but can no longer be kept lit without placing the entire house at risk. Turning off that room may allow the rest of the house to survive longer. But once the temperature inside has fallen too far, no one can know for certain whether its systems will ever work again. For Voyager 1, the situation is even more severe because no one is standing beside it to inspect the circuits, warm the components, or replace a part that has grown old. If LECP is switched off and gradually cools in space, restarting it later may no longer be possible. This is not simply a matter of flipping a switch and waiting for a convenient moment to turn it back on. A shutdown command may become the final decision ever made for that instrument. After nearly half a century of operation, LECP may never be awakened again. For that reason, the command sent into space was not only a technical procedure, it was also the deliberate ending of one part of Voyager's history. When the signal from Earth finally reached Voyager 1, the spacecraft began carrying out the programmed sequence. The shutdown of LECP did not happen in a single instant. It took more than 3 hours from the moment Voyager received the request. During that time, electronic systems built in the 1970s moved one by one into a new state. No one could watch the process directly, and there was no camera recording what was happening inside the spacecraft. Only engineering data could reveal whether Voyager had completed each step as expected. But even after the process aboard the spacecraft was finished, the mission team on Earth still could not know the result. The reply had to leave Voyager and begin the return journey across nearly 23 hours of empty space. Once again, the people who had sent the command could do nothing but wait. When the faint signal finally reached the large antennas on Earth, the mission team was able to confirm that LECP had stopped operating. No sound accompanied the instrument's shutdown, and Voyager sent no farewell. A system that had worked through the encounters with Jupiter and Saturn and across the boundary of the Sun's influence simply stopped providing data. In return, the electricity it had once consumed became a small measure of safety for the systems that remained. According to current estimates, shutting down LECP could extend the life of Voyager 1 by about 1 year, provided no other major changes occur. Set against a journey of nearly 50 years, a single year may not seem very long, but for Voyager, 1 more year means traveling hundreds of millions of additional kilometers and gathering many more months of data from an environment humanity cannot yet reach directly. It also means many more occasions when antennas on Earth will turn toward the sky and wait to see whether the familiar signal still comes home. Even so, switching off LECP does not stop Voyager's power from continuing to decline. The decision creates only a small amount of room within an electrical budget that is shrinking year by year. Next year, the spacecraft will have less power than it has today. While its components continue to age and temperature remains a constant concern, the mission team may eventually be forced to choose again between an instrument that still has scientific value and the stability of the spacecraft as a whole. That is why the decision to shut down LECP feels both like an attempt to save Voyager and a way of delaying the moment when the spacecraft finally falls silent. If saving, it means restoring Voyager to full operation and allowing it to function indefinitely, then the spacecraft cannot be saved in that sense. No new source of power is waiting somewhere ahead, and no repair mission is following behind. All humanity can do is carefully manage the energy Voyager still has left. But if saving it means helping the spacecraft send one more signal, make one more measurement, and survive beyond its original limits, then every small decision made on Earth is still accomplishing exactly that. Voyager is not being brought home. It is simply being kept alive along the path it is already traveling. Every watt of power saved becomes a little more time, while every instrument switched off represents an unavoidable sacrifice. And every reply that returns after nearly 2 days of waiting is proof that the spacecraft has not yet disappeared completely into silence. The reason Voyager is growing weaker did not begin in 2026. It was present from the day the spacecraft left Earth, built into the very power source that allowed the mission to survive far longer than anyone had expected. To understand why the light inside Voyager is slowly fading, we need to return nearly half a century into the past, to the moment when a spacecraft designed for a mission of only a few years began a journey that would carry it far beyond every limit originally imagined. Voyager is traveling through interstellar space with a computer system far slower than the phone resting beside our beds. What is remarkable is not that the technology has grown old, because every machine ages with time. What is remarkable is that after nearly half a century, Voyager can still receive a command from Earth, understand it, and send a reply home, in a place so distant that a single exchange takes almost 2 days. A machine built in the 1970s is still doing exactly what it was designed to do. In 1977, the world was very different from the one we know today. Personal computers had not yet become common household objects. The internet had not connected billions of people, and smartphones still belonged to a distant future. The engineers who designed Voyager had to work with far less memory, processing power, and electronic capability than we have today. Even so, they were preparing a machine that would have to operate in a place no one could ever reach to repair it. On the 20th of August 1977, Voyager 2 left Earth first. More than 2 weeks later, on September 5, Voyager 1 was launched from a different launch pad. The names sometimes make it seem as though Voyager 1 must have departed first, but they were not chosen solely according to launch date. Voyager 1 followed a faster trajectory and was expected to reach Jupiter and Saturn before its sibling, even though Voyager 2 had left Earth earlier. The two spacecraft were nearly identical when their journeys began. They were built from the same basic design, carried many similar scientific instruments, and were both headed toward the giant planets in the outer solar system. Yet from the earliest parts of their flight paths, their futures were never completely the same. Each planetary encounter altered their trajectories, and those changes gradually sent the two Voyagers in different directions through space. From the outside, Voyager does not resemble the spacecraft often seen in movies. It has no cockpit, no windows, and no long hull designed for people to live inside. Its most recognizable feature is the large dish antenna, shaped somewhat like a white bowl held open in one fixed direction. That dish is Voyager's main pathway for receiving commands from Earth and sending its faint data back home. Throughout the journey, the antenna has to remain pointed almost precisely toward Earth. A large enough error could cause the signal to miss the receiving stations on the ground. So even while Voyager travels through an immense expanse of space, it must always know where its former home lies. It does not see Earth as a blue sphere, but its control system must still preserve a line of communication across billions of kilometers of darkness. Several long arms and booms extend from Voyager's main body. Some sensors were placed far from the spacecraft, so they would not be disturbed by magnetic fields or electrical interference created by the equipment on board. Other instruments were positioned where they could observe the surrounding environment without being blocked by the antenna dish. Every location on the spacecraft had a purpose, because once Voyager left the launch pad, no one would ever have another chance to move a sensor by even a few centimeters. At the end of another boom are 3 devices shaped like black cylinders. These are radioisotope thermoelectric generators, the power source that has kept Voyager operating for decades. They are not like ordinary batteries that can be recharged after running low. Inside them is plutonium-238, a material that produces heat as it slowly decays over time. That heat is converted into electricity for the computers, communication system, heaters, and scientific instruments. It can be imagined as a remarkably durable coal stove, burning slowly for many years without ever needing to be refueled. But its fire does not remain equally hot forever, and the system's ability to turn heat into electricity also declines as its components age. From the moment Voyager left Earth, its energy clock had already begun counting down. The engineers did not choose solar panels because Voyager was meant to travel to places where sunlight becomes extremely weak. Near Earth, sunlight is strong enough to power many spacecraft, but the farther they travel, the more rapidly the available light fades. At the distances of Jupiter, Saturn, and beyond, solar panels built with 1970s technology would have needed to be enormous to provide enough energy. Carrying its own power source was therefore the more practical choice for a journey to the outer planets. No one in 1977 could know exactly how long Voyager would survive. The original primary mission focused on flying past Jupiter and Saturn over the course of several years, while anything beyond that depended on the condition of the spacecraft after each stage. Voyager 2 was later sent onward to Uranus and Neptune, but those journeys could not be treated as certain from the beginning. Each new phase became possible only after the previous one had been completed, and the spacecraft was still healthy enough to continue. Voyager was therefore not built with a promise that it would operate for nearly 50 years. The engineers simply tried to create a machine reliable enough to complete its mission in an environment where mistakes could not be forgiven. They used backup systems, tested components carefully, and prepared for many of the situations the spacecraft might encounter. That caution created a foundation far stronger than the mission's original expected lifetime required. Still, good design is only part of the story. Voyager has survived for so long because of thousands of decisions made after it had already left Earth. Whenever an instrument showed signs of trouble, engineers had to understand the problem through extremely limited streams of data. They could not see a loose wire or a component beginning to overheat. They had to infer what was happening from changes in voltage, temperature, and signal behavior. Some problems were solved by switching to backup components. Others required the spacecraft to reuse a system that had been inactive for years, or to change the way it carried out a familiar task. At times, engineers had to write new command sequences for a computer built before many members of today's mission team were even born. The work was like repairing an antique clock from across an ocean, guided only by the faintest sounds coming from inside its casing. Voyager's computers can process about 8,000 instructions per second. That was once enough to control one of the most ambitious missions of its era, but today it is far below the capability of a smartphone. A modern phone can perform billions of operations in the same amount of time. The comparison does not make Voyager seem inadequate. Instead, it reveals how extraordinary its achievements have been with such limited resources. Voyager also does not need to perform the kinds of tasks expected of a modern phone. It does not display high-resolution video, run many applications, or connect to thousands of services at once. Its onboard computers focus on a small number of specific responsibilities, including maintaining orientation, controlling instruments, storing data, and communicating with Earth. That relative simplicity is one reason the system has been able to remain stable for so long. But simple does not mean easy. Voyager must respond on its own to certain situations, because humans cannot send instructions the moment a problem appears. If the spacecraft detects that its voltage, temperature, or orientation has moved beyond safe limits, programs prepared long ago can place it into a protective state. During the long wait for commands from Earth, those automatic decisions may be the only thing preventing a small malfunction from becoming a serious failure. Today, some of the people caring for Voyager were not yet alive when the spacecraft was launched. They work with documents, software, and experience passed down from earlier generations of engineers. Some have spent much of their careers working with a spacecraft that cannot be seen through any ordinary telescope. Their connection to Voyager exists through extremely faint radio signals and records written many decades ago. While the team on Earth has changed over time, Voyager still carries nearly all of its original hardware. It has never been brought back to a factory for a new computer. No one has replaced the antenna, cleaned the connectors, or installed a younger power source. Most of what is operating today is still what left Earth in the summer of 1977. That makes every malfunction unique. When a component stops responding, the mission team cannot order a replacement and send it out. When an area of memory becomes unreliable, they must find a way around it, using the same aging system that is already experiencing the problem. When a heater is turned off to save power, they must accept that nearby components may fall below temperatures ever tested on Earth. Voyager has survived not because some immortal part exists inside it. It has survived because many components have lasted far longer than expected, while weaker parts have been isolated or replaced by another method. The mission has been extended one step at a time, not through a single dramatic decision. Every additional year of operation is the result of the original design, a measure of good fortune, and a great deal of quiet work on Earth. Over time, the way the spacecraft is used has also changed. The cameras that once photographed the planets were switched off when there were no longer any nearby worlds to observe. Scientific instruments have gradually been selected according to how much power they consume and how valuable their remaining data may be. Voyager has changed from a spacecraft that observed worlds through images into a small measuring station sensing interstellar space through magnetic fields, plasma, and high-energy particles. The transformation is a little like an explorer who has traveled too far to keep carrying every tool brought at the beginning. Along the way, that explorer must leave behind what is no longer needed and preserve the instruments best suited to the terrain ahead. But Voyager cannot decide for itself what should remain. Every choice has to be calculated on Earth, sent across the darkness, and followed by a wait of almost 2 days before anyone knows the result. Judged only by its age, Voyager may be considered a very old machine. But age here is more than the number of years since launch. It is also the number of heating and cooling cycles the spacecraft has endured, the radiation it has absorbed, the maneuvers it has performed, and the communications link it has maintained across an ever-growing distance. Every additional day of operation is another day that the original hardware must survive under conditions no test on Earth could fully reproduce over nearly half a century. Perhaps the strangest thing is that Voyager has no idea it has become a symbol. Its computers have no concept of history, records, or human wonder. The spacecraft simply receives signals, checks commands, controls its instruments, and sends data home. The endurance we see is really the result of electrical circuits continuing to perform the tasks assigned to them long ago. From Earth, Voyager is often described as a lonely spacecraft among the stars. Technically, however, it has never been completely abandoned as long as communication remains possible. Ground antennas continue to point toward its location, while teams of engineers monitor every subtle change in the data. The distance between them is immense, but that fragile radio thread has not yet broken. Even so, every design has limits. The power supply continues to weaken, the components continue to age, and there is no way to return Voyager to the condition it was in during 1977. Humanity cannot stop time from passing. It can only use the time that remains as carefully as possible. Keeping one instrument alive for another year may mean that another must be switched off sooner. Nearly 50 years ago, no one could be certain that Voyager would still answer in 2026. The people who built the spacecraft knew only that, if everything went well, it might fly past planets humanity had previously seen only from a great distance. They could not know that its antenna would one day transmit from beyond the boundary of the solar wind. Nor could they know that computers capable of 8,000 instructions per second would continue operating in a world surrounded by devices millions of times faster. Voyager has not survived because of a single miracle. It has survived because of choices made carefully during its design, because of backup systems, and because generations of people have never stopped listening. The spacecraft cannot be brought back to a workshop, yet it is still repaired through commands, traveling across billions of kilometers. Every reply from Voyager is therefore more than scientific data. It is also a sign that a design from the previous century is still resisting the slow erosion of time. Voyager was built to travel to the outer planets, not to survive forever in interstellar space, yet to reach Jupiter, Saturn, and beyond. The two spacecraft took advantage of a rare path created by the motion of the giant worlds. That opportunity does not appear often, and once missed, humanity would have to wait a very long time for a similar arrangement. It was this unusual route that sent the two Voyagers away from Earth with the same basic design, then gradually carried them toward entirely different regions of space. Voyager did not carry enough fuel to propel itself from one planet to the next. The distances between the worlds of the outer solar system were simply too vast, and the amount of fuel required would have made the spacecraft far too heavy from the moment it left the launch pad. So Voyager's journey was not built around the power of its engines, but around the motion the planets already possessed. Each flyby became part of the path leading to the next encounter. In the late 1970s, the four giant planets occupied an unusually favorable arrangement. Jupiter, Saturn, Uranus, and Neptune were not aligned in a straight line, but the spacing between them allowed a spacecraft to visit several worlds in sequence through a chain of connected trajectories. Such an opportunity does not appear often, because each planet moves around the Sun at a different speed. Voyager left Earth just as that rare orbital window was opening. The launch vehicle handled only the first part of the journey, carrying the spacecraft away from Earth and placing it on a path toward Jupiter. After that, Voyager spent most of its time coasting freely, with little need for continuous engine burn. As it approached a planet, gravity began to curve its path. The spacecraft fell toward the giant world, swept past at a carefully calculated distance, and then departed in a new direction. While Voyager was passing by, the planet continued moving around the Sunday. For a brief time, that motion pulled on the spacecraft's trajectory, changing Voyager's speed relative to the Sunday. A small amount of orbital energy was transferred to the spacecraft, while the planet lost an amount so tiny that it could never be noticed. After the encounter, Voyager continued onward at greater speed, already placed on a path toward its next destination. Everything depended on precision. A slight error during the approach to Jupiter could have caused the spacecraft to miss Saturn years later. Engineers had to calculate not only where each planet was when Voyager launched, but where it would be on the day the spacecraft arrived. Those calculations connected every encounter into a single journey stretching across billions of kilometers. Each planet was both a destination and a doorway into the next part of the mission. Jupiter was the first world waiting for both Voyager spacecraft in the outer solar system. From Earth, the planet had been observed through telescopes for centuries, but distance still concealed much of the detail in its atmosphere and around its moons. As Voyager approached, a point of light slowly expanded into an enormous sphere, wrapped in bands of swirling clouds. The new images revealed an atmosphere in constant motion. Bright and dark regions stretched in parallel around Jupiter, torn, twisted, and bent by powerful winds. The Great Red Spot appeared as a storm larger than Earth, one that had endured longer than any weather system humanity had ever monitored. Voyager did not discover the storm, but its close view revealed smaller structures within and around it. Jupiter was no longer simply a vast ball of gas. It had become a world of complex weather. Near the planet, Voyager also found a very faint ring, difficult to detect beside the famous bright bands surrounding Saturn. Tiny particles scattered through space reflected so little light that they had remained almost hidden from ordinary observations. The discovery added another feature to the largest planet in the solar system. But an even greater surprise appeared on one of the moons orbiting nearby. From a distance, Io had looked like little more than a small point of light. When Voyager's images were transmitted to Earth, scientists noticed plumes of material rising high above the surface. They were not signs of impacts or flaws in the images, but eruptions taking place in real time. A moon far from the sun was alive, with intense volcanic activity. Io's heat does not come mainly from sunlight. Jupiter and the neighboring large moons continually pull Io in slightly different directions, causing its interior to flex during every orbit. That process generates heat and sustains the geological activity on its surface. After Voyager's images, moons could no longer be regarded simply as cold pieces of rock accompanying their parent planets. The encounter with Jupiter ended far more quickly than the journey required to reach it. Voyager had only a brief window for observation before the planet's gravity bent its course towards Saturn. Behind it, the immense cloud bands and orbiting moons gradually shrank back into points of light. Ahead lay many more months of drifting through empty space, where the next destination remained too distant for the cameras to see clearly. Saturn appeared with its broad, luminous ring system surrounding the planet, like thin lines drawn across the darkness. As Voyager moved closer, the rings no longer looked like a few continuous bands. They separated into countless narrow layers, gaps, and interwoven structures. The material within them consisted of pieces of ice and rock orbiting together around the planet. Voyager passed close enough to reveal that the ring system was far more delicate and complex than observations from Earth had ever suggested. For Voyager 1, however, the target that would determine its future trajectory was not the rings, but Titan. Saturn's largest moon was wrapped in a dense atmosphere, something rarely found around a body of its size. The cameras could not see through the orange haze to the surface below. That very obscurity made Titan important enough to justify sacrificing the remainder of Voyager 1's planetary journey. Voyager 1 was directed close to Titan to study its atmosphere and the environment surrounding the moon. The encounter returned valuable data, but the gravity of Titan and Saturn changed the spacecraft's path in a way that could not be reversed. After leaving the Saturn system, Voyager 1 was deflected above the plane in which most of the planets travel. The route to Uranus and Neptune was closed. This was not the result of a mistake. Scientists chose to prioritize Titan because its thick atmosphere raised questions that no other known moon could answer at the time. In exchange, Voyager 1 ended the planetary phase of its journey after Saturn and began following a path of its own. That new trajectory carried it away from the central region of the solar system faster than Voyager 2. Voyager 2 remained on a route closer to the plane of the planets. After completing its flybys of Jupiter and Saturn, the spacecraft's condition was evaluated before the mission was extended. Its instruments were still functioning, its control systems remained stable, and enough power was available for the next stage. Instead of ending at Saturn, Voyager 2 was directed toward a world no spacecraft had ever visited. In January 1986, Uranus began to fill the frames. The planet rotates almost on its side, with an axis tilted in a way unlike most other worlds. At times, its poles point nearly toward the sun, causing its seasons and sunlight to unfold in a very unusual rhythm. Voyager flew past only once, but those brief hours of observation remain the closest view humanity has ever had of the planet. At the distance of Uranus, sunlight was already far weaker than it is near Earth. Dark rings and small moons appeared under difficult viewing conditions, forcing the cameras and instruments to make use of every opportunity. The data was not enough to explain the planet's entire structure or atmosphere. Even so, it transformed a pale blue sphere, seen through telescopes, into a world with its own distinct character, one that could never be replaced by distant speculation alone. After Uranus, Voyager 2 continued traveling for more than 3 years. Neptune was so distant that the sun, seen from there, looked like little more than an intensely bright source in the sky, no longer carrying the familiar presence it has from Earth. Many had expected to find a cold, dark planet that was almost motionless. Instead, the images revealed an atmosphere filled with movement. Neptune's deep blue color was crossed by bright clouds and vast swirling regions. Its winds moved at some of the highest speeds ever measured on any planet. Even though Neptune receives very little energy from the Sunday, heat from within the planet, together with the structure of its atmosphere, appeared sufficient to sustain powerful weather. Voyager 2 passed by only briefly, but that short encounter shattered the idea that great distance must always mean stillness. Triton, Neptune's largest moon, brought another surprise. Its surface was cold enough for many substances to exist as ice, yet plumes of material were still rising above it. That activity showed that even a frozen world at the edge of the solar system might not be completely motionless. Beyond Triton, there were no more major planets waiting along Voyager 2's path. The Neptune encounter brought the exploration of the 4 giant planets to a close. Voyager 2 became the only spacecraft ever to pass close to Jupiter, Saturn, Uranus, and Neptune during a single journey. To this day, it remains the only spacecraft to have observed the 2 most distant planets from close range. Much of what humanity knows directly about Uranus and Neptune still depends on a few hours of data collected many decades ago. The flybys left behind more than images and measurements. They shaped the long-term paths of both Voyager spacecraft after the planetary phase of the mission ended. Titan sent Voyager one above the main plane of the solar system, while Neptune pushed Voyager 2 inches another direction below it. The 2 spacecraft had been nearly identical when they left Earth, but they continued to move farther apart along paths that would never cross again. The remaining control fuel was enough only for small adjustments. It could not bring Voyager back or redirect it toward an entirely new destination. The trajectories they follow today are the result of encounters that took place decades ago. A tiny change near Jupiter was magnified across billions of kilometers, placing the spacecraft in a different position by the time it reached Saturn. Even tens of thousands of years from now, the effects of those choices will still be present in their paths among the stars. Each planetary encounter occupied only a very small part of the journey, yet its influence lasted for almost the entire remaining life of the spacecraft. Voyager could not stop to study a world for longer, nor could it turn back when a discovery made scientists wish for another look. It had only one passage, a brief window in which to gather data, and a single opportunity to choose the correct direction. Then the planet quickly receded behind it. When Voyager 2 left Neptune in 1989, no more large worlds were waiting ahead. By then, Voyager 1 had already been traveling away from Saturn for nearly a decade, and both spacecraft were beginning a very different kind of mission. The cameras that had observed the planets were still functioning, but there were no nearby targets left to photograph. The darkness ahead promised no more spectacular flybys. Before those cameras were switched off to conserve power, Voyager 1 received one final request from Earth. The spacecraft was not told to look deeper into the darkness ahead. Instead, it was asked to turn back, point its cameras toward the path it had already traveled and photograph the family of planets surrounding the Sunday. In that distant image, Earth had become a point of light so small that it nearly disappeared. In 1990, Voyager 1 turned its camera toward Earth for the last time. From where the spacecraft was traveling, our planet no longer appeared as a blue sphere wrapped in white clouds and deep oceans. It occupied only a tiny fraction of a single pixel, so small that it could easily disappear within the scattered light of the Sunday. After that sequence of images, Voyager 1's cameras were switched off and never took another photograph. When it received the command to look back, Voyager 1 was about 40 times farther from the Sun than Earth is. Saturn had been left behind nearly a decade earlier, and the planets that had once filled its frame were now only distant points of light. No large world waited ahead to be observed from close range. The part of the mission devoted to planetary photography had reached its end. The request from Earth asked the spacecraft to do something temporarily opposed to the direction of its journey. Voyager 1 had to rotate its entire body, pointing its cameras back toward the region of sky where the Sun and the planets it had visited remained behind. From that distance, it could not capture the entire solar system in a single frame. Many separate images had to be recorded and later assembled into a much wider portrait. This sequence of observations became known as the family portrait of the solar system. In it, several planets appeared as tiny points of light, scattered across dark frames. The cloud bands of Jupiter were gone, along with the sharply defined rings of Saturn and the distant storms of Neptune. Distance had reduced all those worlds to faint traces of light surrounding a single star. Earth appeared within a dim beam stretching across the image. The beam was not a real pathway through space, but the result of sunlight scattering inside the camera system. Within that glow, our planet was only a pale point, nearly impossible to recognize unless someone showed exactly where to look. The image later became known as the pale blue dot. From that distance, no ocean could be distinguished. The continents, cities, mountains, and every border drawn by human beings had vanished from the frame. Everyone alive at the time, along with every person who had ever lived before them, existed on that same tiny point. The image needed little explanation to reveal how profoundly distance can change the way a world is seen. Carl Sagan was one of the people who strongly encouraged the idea of having Voyager turn back to take this portrait. He understood that the images would offer little new scientific detail about the surfaces of the planets, because they were already so far away. Their value lay in a perspective no spacecraft had ever returned before. The solar system was being seen not from the surface of one of its planets, but from a machine already on its way out of the region of familiar worlds. The image of Earth is often remembered as a symbol of humanity's smallness, yet its meaning does not need to become a long philosophical reflection. Voyager simply recorded what its camera could actually see from that distance: a very faint planet within an immense region of space. The emotion arises naturally from the contrast between the size of that point of light and everything humanity knows exists upon it. The images from 1990 also marked an important transition in the life of Voyager 1. From that moment onward, the spacecraft would no longer operate as a planetary observer through images. The major targets were behind it, while nothing ahead was close enough for the cameras to provide comparable value. A system that had allowed humanity to see volcanoes on Io and delicate rings around distant planets was about to be retired forever. The cameras required electricity to operate, and some of their internal components had to be kept warm. During the early years, that power was a reasonable part of the mission, because every planetary encounter could produce thousands of new images. Once Voyager entered a region with no nearby planets, the value of the cameras declined while the spacecraft's power supply continued to weaken. Keeping the imaging system active would have taken energy away from instruments better suited to the journey ahead. Voyager's memory was also extremely limited compared with modern devices. Image data occupied a great deal of storage and required a long time to transmit. especially as communication rates continued to fall with distance. Measurements of magnetic fields, plasma, and charged particles could be collected in smaller data packages while directly supporting the interstellar mission. So the cameras were not switched off because they suddenly failed, but because the remaining resources could be used more effectively elsewhere. After the final photographs, the software needed to operate the cameras was no longer maintained in the spacecraft's computers. The heaters that had once protected the optical system were also turned off to conserve power. Over the decades, the temperature of those components has fallen to levels at which they were never designed to resume operation. Even if enough electricity were available for an attempt, no one knows whether the cameras could still respond after lying cold in space for so long. Voyager is therefore not quietly taking new photographs and storing them on board, nor is it sending back dark images of interstellar space, as people sometimes imagine. Both spacecraft stopped using their cameras long ago, and imaging software no longer plays a role in the present mission. What Voyager sends home today consists mainly of numbers, graphs, and engineering signals. The loss of the cameras did not mean that Voyager became completely unable to sense its surroundings. Instead of visible light, other instruments continued measuring phenomena that human eyes cannot observe directly. Magnetic fields passed through the spacecraft's location. High-energy particles struck its sensors, and the plasma around it produced extremely weak oscillations. Each measurement revealed part of the environment Voyager was moving through. A person entering a room without light can still recognize many things without seeing the objects inside. Cold or warm air can be felt against the skin. Echoes can suggest whether the room is large or small, and a faint current of air may reveal an open door somewhere nearby. Voyager also continued onward, without needing to create a direct image of everything around it. Its remaining instruments allowed the spacecraft to sense the environment through signs other than sight. The comparison is only accurate up to a point, because Voyager does not experience sensation as a human does. It does not hear, touch, or perceive the space around it in the ordinary sense. Its sensors simply respond to physical changes and convert them into data that can be transmitted to Earth. It is the people on Earth who assemble those signals and imagine the environment through which the spacecraft is passing. The space ahead of Voyager is not an absolute emptiness. The density of matter is extremely low, but atoms, electrons, high-energy particles, and magnetic fields are still present. They are far too sparse to form clouds or surfaces that an ordinary camera could photograph. Yet, when they pass through sufficiently sensitive detectors, they leave measurable traces. A photograph often feels more immediate because the viewer can recognize shapes, colors, and motion at once. Data about particles or magnetic fields is not as easily understood, because it usually begins as a sequence of numbers. Scientists must watch how those values rise, fall, or change direction over time. From variations that may appear very small, a vast boundary in space can gradually emerge. For many years after its cameras were turned off, Voyager 1 had not yet truly entered interstellar space. It continued traveling through the outermost region still strongly influenced by the sun, where the solar wind became weaker and began to change in character. No image announced that the spacecraft was approaching a boundary. Only invisible measurements revealed that the surrounding environment was becoming different. Particles originating from the sun began to appear less often. At the same time, high-energy particles arriving from the rest of the galaxy became more common around the spacecraft. The magnetic field did not disappear, but its direction and strength offered additional clues about the region Voyager was crossing. Each instrument provided one fragment of evidence, and no single fragment could tell the entire story on its own. Even if the cameras had still been operating, they would have struggled to photograph this boundary as a glowing wall. The place where the influence of the solar wind gives way to the interstellar environment has no solid surface and no clearly visible color. The spacecraft could cross it without seeing any dividing line ahead. Only changes in the particles and fields around it could reveal that one region was ending and another was beginning. From this point onward, Voyager's role became very different from what it had been in the early years. It no longer returned images that allowed the world to instantly recognize a planet from close range. The data arrived more slowly, was harder to visualize, and often required months of analysis before its meaning became clear. In return, the spacecraft was making measurements in a place where no other human-made instrument had ever operated directly. The final photograph was therefore not the end of the mission. It only brought Voyager's era of observing the solar system through visible light to a close. After 1990, the journey continued with instruments that were less visually dramatic but far better suited to the space ahead. The spacecraft could no longer show us where it was going, but it could still tell us what that place contained. The pale blue dot remained as the final memory from Voyager 1's eyes. In that image, Earth lay behind the spacecraft, while most of the unknown journey still stretched out ahead. From the day the cameras were switched off, Voyager never looked back through images again. Every sign that followed came from the invisible sensors mounted on the spacecraft since 1977. Years later, those instruments began detecting changes that no camera could ever have seen. The wind from the sun slowed. Particles from beyond the solar system became more common, and the environment around Voyager changed step by step. The spacecraft was approaching a boundary that appeared in no photograph. There, the region shaped by the sun gradually gave way to the matter between the stars. There was no sign announcing that Voyager had left the region influenced by the solar wind. No glowing line appeared ahead, and no impact marked the moment when the spacecraft passed from one place into another. Everything around Voyager remained dark, cold, and almost unchanged when viewed through a camera. The boundary emerged only gradually in the numbers, as the particles surrounding the spacecraft began to behave differently. The sun sends more than light and warmth toward the planets. From its outer atmosphere, a continuous stream of charged particles escapes and spreads outward in every direction. This flow of matter is called the solar wind, although it is nothing like the moving air we feel on Earth. In the near vacuum of space, protons, electrons, and magnetic fields still race outward at hundreds of kilometers per second. Earth, Mars, Jupiter, and the more distant planets all lie within this flow. The solar wind passes over them, interacts with magnetic fields, and sometimes produces storms that can affect satellites or create auroras. As it moves farther from the sun, the stream of particles spreads across an increasingly large region. Yet its influence does not disappear immediately beyond the orbit of the last planet. The sun and its planets are moving through the matter that exists between the stars. As they travel, the solar wind creates an immense region surrounding the planetary system, commonly known as the heliosphere. Simple illustrations sometimes show it as a bubble, but its true shape is neither perfectly round nor fixed. Pressure from the interstellar environment, magnetic fields, and the changing activity of the sun continually cause its boundaries to expand, contract, and deform. Most of Voyager's early life unfolded deep inside the heliosphere. There, the solar wind continued moving outward at high speed, carrying traces of the star that had created it. Instruments aboard the spacecraft measured particles originating from the sun and tracked how they changed over time. Even after Voyager had traveled beyond every planet, it still had not escaped the region dominated by the solar wind. As the stream of particles approached the outermost reaches, it began to encounter pressure from the matter between the stars. The solar wind could not continue expanding forever with the same speed and density. It gradually slowed, heated up, and became more turbulent. This first transition region had no solid surface, but the changes were clear enough for Voyager's instruments to detect. Voyager 1 reached this area in late 2004. Measurements showed that the solar wind slowed dramatically as the spacecraft crossed a boundary known as the termination shock. The name may suggest a sudden and violent event, but Voyager was not struck or shaken like a vehicle passing through a wall. the change occurred mainly within the plasma surrounding it. Beyond the termination shock, Voyager entered a new region between the slowing solar wind and the outer boundary of the heliosphere. This area is known as the heliosheath, where particles from the sun are still present but no longer move outward in the simple way they once did. They become compressed, redirected, and mixed within a more complex environment. Voyager 1 continued traveling through this region for years without knowing exactly how far away the outer edge might be. No one could place a marker ahead of the spacecraft to announce the day it would cross the final boundary. Models on Earth could offer only estimates, because the shape of the heliosphere depends on many factors that had never been measured directly. Solar activity also changes in cycles, causing the pressure of the solar wind to strengthen or weaken. The boundary ahead was therefore not standing still while Voyager approached. During this period, the instruments began recording short-term changes. The number of particles originating inside the heliosphere would sometimes fall and then rise again. Cosmic rays arriving from outside would increase for a time before returning to earlier levels. These fluctuations led scientists to wonder whether Voyager was touching an unstable edge or merely passing through temporary structures. The summer of 2012 brought much clearer signs. Energetic particles created or trapped within the sun's region of influence dropped rapidly. At the same time, cosmic rays arriving from the rest of the galaxy increased and remained at high levels. The environment around Voyager 1 was no longer changing for only a few hours before returning to normal. It appeared to have entered an entirely new state. Even then, the research team did not immediately announce that Voyager had entered interstellar space. One important plasma instrument was not operating in the direct way they had hoped, making it difficult to confirm the electron density around the spacecraft at once. The magnetic field also did not change direction as sharply as some models had predicted. The evidence seemed to point toward the same conclusion, but certain details did not fully match expectations. The final answer came from an event that had occurred on the Sun many months earlier. A powerful eruption had sent a shock wave outward, and by 2013, that wave finally passed Voyager's location. The plasma wave instrument recorded extremely faint oscillations in the surrounding environment. From their frequency, scientists inferred that the density of matter around the spacecraft was higher than the levels usually found inside the heliosphere. That data helped confirm that Voyager 1 had entered the interstellar environment. After the full sequence of measurements was reviewed, the date of the heliopause crossing was identified as the 25th of August 2012. The heliopause is the boundary where pressure from the solar wind no longer dominates over the environment between the stars. The spacecraft crossed it without any moment that could be seen by the human eye. This announcement is often simplified by saying that Voyager 1 had left the solar system. The phrase is easy to understand, but it is not completely accurate under every definition. The spacecraft had left the heliosphere and entered interstellar space, but the sun's gravity was still acting upon it. Many more distant bodies, including objects within the Oort cloud, are still considered part of the wider solar system. The Oort cloud is thought to be a vast region containing countless icy objects far beyond the planets. Its outer boundary may lie tens of thousands of times farther from the sun than Earth does. Voyager would need hundreds of years to reach the inner portion of this region, and tens of thousands of years to pass through it completely. For that reason, entering interstellar space and escaping every influence of the sun are not the same thing. What Voyager crossed was the boundary of the flow of matter and pressure created by the Sunday. On the other side, the environment surrounding the spacecraft was shaped more strongly by the space between the stars. Even so, the sun remained the body governing most of Voyager's long-term trajectory during this stage of the journey. The spacecraft did not suddenly become part of another star system after the 25th of August 2012. 6 years later, Voyager 2 also approached the edge of the heliosphere from a different direction. It did not follow Voyager 1's path, nor did it cross through exactly the same region. Conditions differ slightly in every direction around the sun, much like two boats leaving a broad body of water. through distant shores. Voyager 2's data therefore became a rare opportunity to compare two separate parts of the boundary. In late 2018, instruments aboard Voyager 2 recorded a sequence of changes that resembled, but did not completely match, what Voyager 1 had observed years earlier. Particles originating inside the heliosphere dropped sharply, while cosmic rays from beyond it increased. Voyager 2's plasma instrument was still operating, allowing the density of matter around the spacecraft to be measured more clearly. The 5th of November 2018 was identified as the date when the second spacecraft crossed the heliopause. Voyager 2 crossed the boundary at a slightly different distance from the Sun than Voyager 1. The patterns of particles, plasma temperature, and magnetic fields were not identical either. Those differences showed that the heliosphere is not a symmetrical shell surrounding the Sunday. It contains folds, compressed regions, and structures that vary according to direction, motion, and conditions in the interstellar environment. 2 measurement points are still far too few to map the exact shape of a region stretching across tens of billions of kilometers. Voyager 1 and Voyager 2 are like 2 tiny needles, touching widely separated points on an enormous surface. Their data allows scientists to test many models, but it cannot provide a complete outside view of the heliosphere. Whether its shape is elongated, compact, or strongly asymmetrical remains an open question. Even the idea of a boundary becomes more complicated when examined closely. The heliopause is not an infinitely thin layer. It may contain interwoven regions of particles and magnetic fields. Matter from inside can sometimes escape outward, while influences from the interstellar environment may reach into certain areas within. Voyager revealed the transition, but it did not turn it into a clearly drawn line on a map. The crossing dates were also determined only after the data had been transmitted to Earth and analyzed. Voyager did not send an announcement saying it had just entered interstellar space. Its instruments simply continued recording the environment around the spacecraft, just as they did every day. On Earth, several teams had to combine changes in particles, plasma, and magnetic fields before the conclusion became strong enough to accept. That method of discovery reflects the true nature of much of space science. Major turning points do not always appear in spectacular images. Sometimes they remain hidden within a curve that has only slightly changed its slope. One number falls, another signal rises, and several measurements begin telling the same story. The boundary of the Sun became visible only after people patiently learned to read traces that could not be seen. Since crossing the heliopause, both Voyager spacecraft have continued traveling through the interstellar environment near the Sunday. The word interstellar can create the impression that they are already moving among distant stars, but the nearest star remains unimaginably far away. Voyager has not approached another planetary system, nor is it heading directly toward any known world. It is simply moving through the thin matter that fills the space within our galaxy. That environment is not completely isolated from the Sunday. Powerful solar eruptions can still send shockwaves beyond the heliopause, reaching Voyager months or even years later. As these ripples pass through, the interstellar plasma oscillates and produces signals that instruments aboard the spacecraft can record. The Sun can therefore still touch Voyager, even though its wind no longer dominates the surrounding space. At the same time, cosmic rays from the galaxy can now reach Voyager without being shielded by the heliosphere in the same way as before. These high-energy particles carry information about processes occurring far beyond the region of the planets. From Voyager's position, scientists can directly measure an environment that spacecraft near Earth can only study indirectly. This is why the instruments that remain active become even more valuable as the available power continues to decline. Crossing the heliopause did not end the exploration. It opened a new mission. Voyager was no longer primarily telling humanity about Jupiter, Saturn, or worlds that could be photographed by a camera. It began describing the region where our star meets the rest of the galaxy. The questions there are less visually dramatic. but they are directly connected to how the sun protects and interacts with the environment around it. That invisible boundary also reveals how little humanity still knows about the space close to home. Thousands of exoplanets have been discovered around distant stars, while the exact shape of the heliosphere has yet to be fully measured. Two machines, built in 1977, are providing the first data points from the other side. No newer spacecraft is currently able to replace their positions anytime soon. When Voyager moved beyond the region dominated by the solar wind, it did not enter an empty void with nothing left to measure. Matter, magnetic fields, cosmic rays, and extremely faint plasma waves still surround the spacecraft. A camera could not turn them into a visible landscape, but the remaining sensors continue to detect their smallest changes. Those invisible signals are the reason NASA is still trying to keep Voyager operating for as long as possible. If a person could stand beside Voyager, they would not see glowing clouds or streams of matter drifting past. The sky would remain dark. There would be no air to carry sound to their ears, and the surrounding particles would be too small and too sparse to form any visible scene. Even so, the spacecraft's instruments continue to detect a very real environment. It is far too thin for a human hand to touch, but never too empty for the most sensitive sensors to measure. Beyond the heliosphere, stillness does not mean that all activity has stopped. Charged particles continue to move, magnetic fields extend through space, and layers of plasma oscillate when disturbed by a wave arriving from far away. No sound travels through the vacuum like wind or water on Earth. Voyager detects only extremely subtle physical changes, which are then converted into streams of data and transmitted home. Most of this information does not immediately appear as an image that is easy to understand. Scientists study graphs changing over time, numerical measurements of density, and signals indicating that a particle has just passed through a detector. A single day of data may contain no major discovery, recording an environment much like the one observed the day before. But when those measurements continue for months and years, slow changes begin to reveal the structure of interstellar space. One of the first questions concerns the direction of the magnetic field around Voyager. A magnetic field does not glow, nor does it form a visible line stretching out in front of the spacecraft. The magnetometer records only the field's strength and the direction of its influence at Voyager's location. From those continuous measurements, scientists can track how the environment beyond the heliosphere differs from the solar wind through which Voyager once traveled. The sun's magnetic field is carried outward by the solar wind, creating an immense structure that extends throughout the heliosphere. Beyond it, Voyager encounters the magnetic field of the local interstellar environment, associated with the region of matter through which the entire solar system is moving. The two systems are not completely separated like rooms divided by a sealed wall. They are compressed, bent, and brought into contact near the boundary that both Voyager spacecraft eventually crossed. The first data from Voyager 1 caused some confusion, because the direction of the magnetic field did not change as sharply as some predictions had suggested. Particle measurements showed that the spacecraft had entered a new environment, yet the magnetic field seemed to retain a relatively familiar orientation. That detail forced scientists to reconsider how the heliosphere meets interstellar space. The sun's outer boundary proved to be far more complicated than a simple shell drawn as a smooth curve. The next question concerns how much matter actually exists around the spacecraft. Interstellar space is extremely thin, but neutral atoms, ions, and electrons are still distributed across the vast distances between the stars. A small container on Earth holds far more particles than the same volume of space around Voyager. Yet when an instrument is sensitive enough and has enough time to observe, even that low density leaves a measurable signal. Voyager does not carry a container that gathers plasma and counts each particle inside. Instead, the plasma wave instrument monitors how electrons in the surrounding environment oscillate when they are disturbed. The frequency of those oscillations is related to the electron density at the spacecraft's location. This allows scientists to determine how dense or sparse the space around Voyager is, without having to capture all the matter passing by. Plasma is often called the fourth state of matter, though that name can make the idea sound more unfamiliar than it needs to be. In plasma, some atoms have lost electrons, creating a mixture of charged particles that can respond to magnetic fields. The sun, the solar wind, and much of the visible matter in the universe contain plasma in many different forms. Voyager is simply traveling through an extraordinarily thin version of that environment. When a powerful eruption on the sun sends a shock wave outward, the signal does not reach Voyager immediately. It must cross billions of kilometers, pass beyond the boundary of the heliosphere, and continue through the interstellar environment. When the wave finally reaches the spacecraft, the surrounding plasma begins to oscillate in a way the instrument can detect. The data is sometimes converted into an audible range for people to hear, but that sound is a representation of the measurements, not an actual noise traveling through the vacuum. These converted recordings often sound thin, high-pitched, and sustained. They allow the human ear to recognize changes in the signal more easily than it might by looking only at a sequence of numbers. But beside Voyager, no ringing sound echoes through the darkness. The environment oscillates electrically and magnetically, while the spacecraft records those variations in a form suitable for scientific analysis. Plasma signals have shown that the density of matter beyond the heliosphere is higher than in the environment Voyager once crossed inside it. This result was one of the pieces of evidence that helped confirm Voyager 1 had entered interstellar space. Continued measurements have also shown that the density does not remain perfectly constant as the spacecraft travels farther. There are regions of slight increase, periods of stability, and fluctuations connected to solar activity arriving after a very long delay. A third group of observations comes from high-energy particles. Some were created or accelerated within the Sun's region of influence, while others have traveled much greater distances across the galaxy. They can carry enormous amounts of energy and move close to the speed of light. When they pass through Voyager's instruments, they leave traces that help scientists distinguish their origins and energy levels. Cosmic rays are not beams of visible light. Most are protons, atomic nuclei, and some electrons accelerated by powerful processes within the galaxy. The precise origin of an individual particle cannot be determined from a single detection. Even so, the distribution and energy of large numbers of particles reveal how the environment around Voyager shields them, guides them, or allows them to pass through. While Voyager was still deep inside the heliosphere, it remained within a region where the solar wind and its magnetic field provided some protection from galactic cosmic rays. As the spacecraft approached the heliopause, that influence changed, and the number of particles arriving from outside began to increase. When Voyager 1 crossed the boundary in 2012, particles associated with the Sun dropped sharply, while galactic cosmic rays rose noticeably. That reversal became an important sign that the spacecraft had reached the other side. Particle instruments do not tell their story through a single measurement. They monitor thousands or millions of tiny impacts and gradually build a statistical picture. An individual particle may arrive from many possible directions and carry a history that cannot be traced. Only when the entire flow of particles changes together can scientists recognize that the environment around the spacecraft is entering a different state. LECP was once an important part of that observational ability. For nearly half a century, the instrument monitored ions and electrons at relatively low energy levels compared with many cosmic rays. It operated within Jupiter's magnetic field, near Saturn, throughout the solar wind, and later in interstellar space. LECP's data connected many very different environments into an observational record of unprecedented length. The value of a long data record can sometimes be difficult to recognize on any individual day. A measurement taken in the morning may differ little from one taken in the evening, and an entire new month may add only a few more points to a graph. But over many years, Those small points revealed trends that a brief flyby could never detect. Voyager is not only passing through interstellar space, it is observing the same environment, while its position continually changes. Telescopes on Earth can see galaxies billions of light years away, analyze the atmospheres of some planets beyond the solar system, and follow explosions occurring at enormous distances. Yet no matter how powerful they are, they still observe the interstellar environment near the Sun from inside the region influenced by our own star. Voyager, by contrast, is located directly beyond the heliopause. The difference is between observing something from far away and placing a sensor within the environment being measured. That does not mean Voyager has traveled deep into the vast reaches of the galaxy. Compared with the distances between stars, it remains very close to the Sunday. Light from the nearest star beyond the Sun takes more than 4 years to reach Earth, while Voyager is only about 1 light day away from us. Even so, the spacecraft has crossed a boundary beyond which no other human-made instrument has ever operated for an extended period. Those direct measurements help scientists test how the heliosphere shields the solar system from the galactic environment. They also reveal the density of nearby interstellar plasma, the arrangement of magnetic fields, and how far disturbances from the Sun continue to travel. Each answer uncovers more details that remain uncertain, because the 2 Voyager spacecraft have followed only 2 narrow paths through an immense region of space. Conditions in other directions around the heliosphere still have to be inferred mainly from models. Voyager 1 and Voyager 2 do not measure everything in exactly the same way. Some instruments aboard one spacecraft have stopped working, while similar instruments on the other continue to provide data. The 2 spacecraft crossed the heliopause at different locations and at different times, so the environments they encountered were not completely identical. Those differences help scientists recognize that the Sun's boundary is constantly changing and does not have a simple shape. On many days, the signals Voyager sends home contain only engineering data and very subtle measurements. Not every packet of information leads to a new announcement or a major headline. The importance lies in continuity, because a long gap in the record could cause slow changes to be missed. As long as the spacecraft remains active, even an ordinary day becomes part of a record that can never be recreated later. No replacement spacecraft is traveling just behind Voyager. Even if a new mission were launched in the future, it would require many years or even decades to reach the boundary of the heliosphere. By then, conditions on the Sun and in the interstellar environment may have changed. The data being collected now is therefore rare, not only because of the distance, but also because it records a particular period in the interaction between our star and the galaxy. Every instrument that is switched off removes part of that picture. The magnetometer answers one set of questions. The plasma instrument reveals another aspect, and the particle detectors track flows of matter that cannot replace one another. When an instrument stops operating, the systems that remain can continue working, but they cannot completely fill the gap it leaves behind. Voyager can still sense its surroundings, but the number of senses available to it is steadily diminishing. Shutting down LECP was therefore more than simply retiring a machine that had grown too old. A continuous record extending back to 1977 reached its end, and the measurements it once provided would no longer continue from the spacecraft's present location. The electricity saved helps protect other systems, but the cost is the loss of another way for humanity to listen to interstellar space. Every decision that extends the life of the spacecraft as a whole also narrows the scientific capabilities within it. This trade-off will continue to return as the power supply declines. Engineers must consider which instruments provide the most valuable data, which consume more electricity, and which components must remain warm to prevent a larger failure. No choice can preserve everything as it was. Voyager can continue only by gradually surrendering some of the abilities that made its nearly half-century journey possible. Beyond the heliosphere, the spacecraft is still exactly where scientists would want an observing instrument to be. Every new kilometer carries it farther into an environment that had never been measured directly before Voyager. Magnetic fields, plasma, and cosmic rays continue to pass through the spacecraft, carrying subtle changes from the region surrounding the sun. The space ahead has not become emptier, but humanity's ability to observe it through Voyager is slowly fading. The cause is not a storm pursuing the spacecraft or an unexpected danger appearing ahead. The greatest threat remains the finite supply of energy Voyager has carried since the day it left Earth. Each year, its generators produce less electricity, while every system still operating requires a share of that power. And as the energy budget continues to shrink, every remaining watt will help determine how much longer Voyager can continue listening to interstellar space. 4 watts is only enough to power a small LED bulb in a room on Earth. For Voyager, however, it is the amount of electricity lost each year, power that can never be restored and cannot be replenished from outside. No new solar panel, electrical cable, or charging station is waiting ahead. Every time Earth completes another orbit around the Sun, Voyager's energy budget becomes a little smaller. That power begins with 3 radioisotope thermoelectric generators mounted at the end of a long boom. Inside them, plutonium-238 continues to decay and produce heat, just as it has for nearly half a century. The process is slow, steady, and requires no command from Earth, but the amount of heat produced gradually declines over time, while the materials that convert that heat into electricity cannot preserve their original efficiency forever. The plutonium does not suddenly run out like fuel in a car. It remains inside the generators and continues producing heat, but the amount of useful energy reaching the spacecraft steadily decreases. No software update or remote operation can reverse that decline. No command can make the radioactive material young again or restore converters that have been operating for decades. The total electrical power available aboard each Voyager spacecraft decreases by about 4 watts every year. That amount would seem almost insignificant in a house, where replacing a light bulb or connecting another power source could make everything work again. On Voyager, 4 watts is a meaningful share of an energy supply that is already extremely small. Each time the available power falls, the mission team must search for another place to conserve electricity without taking away the spacecraft's ability to function. Voyager's electricity is not used only by its scientific instruments. The computers need power to read commands, process data, and monitor the spacecraft's condition. The attitude control system must know where the antenna is pointing, while the radio transmitter must remain strong enough to send a signal across tens of billions of kilometers. If those functions stop, even a healthy scientific instrument will have no way to return its data to Earth. Temperature creates another need that is just as important. The space surrounding Voyager is extremely cold, while many components can operate reliably only within a certain temperature range. Heaters are located near scientific instruments, fuel lines, and other sensitive areas to prevent them from becoming too cold. Cutting power to a heater saves electricity immediately, but it may place nearby hardware in conditions that were never tested. The fuel lines used by the attitude control system require particular attention. Voyager uses tiny amounts of propellant to rotate its body and keep the large antenna pointed toward Earth. If the fuel or its lines become too cold, the spacecraft's ability to adjust its orientation could be affected. Voyager might not fail completely, but its fragile communications link with Earth could drift away from the direction it needs to maintain. The remaining power must also be shared among the sensors observing interstellar space. The magnetometer, plasma wave instrument, and particle detectors all require energy to collect and process measurements before passing the data into the communication system. Turning off a scientific instrument can reduce the electrical load, but it also removes part of Voyager's ability to perceive the environment around it. Every watt saved, therefore, comes with something that must be surrendered. During the early years, Voyager had enough electricity to operate its cameras, heaters, and many scientific instruments at the same time. The planetary flybys required the systems to work intensely, collecting images and transmitting large amounts of data back to Earth. After the planetary journey ended, those needs changed. The cameras were among the first systems to be retired because there were no longer any nearby targets worth photographing. Turning off the cameras saved more than the electricity used by the imaging instruments themselves. Their heaters, operating software, and data transmission demands no longer had to be supported as before. The energy could be redirected toward instruments better suited to the interstellar mission. The decision ended Voyager's era of planetary imagery. But in return, the spacecraft was able to continue measuring particles and magnetic fields for decades. As the available power continued to decline, non-essential heaters were gradually switched off. Many components kept working at temperatures lower than their original designers had ever expected. This does not mean they are immune to the cold. It only shows that the hardware has endured beyond the limits established during testing. Each time the temperature falls farther, the mission team must watch carefully for signs that something has begun to behave abnormally. An instrument that survives the cold today may not continue operating after many more years. Materials can contract, electrical connections can change, and lubricants inside moving mechanisms can gradually lose their effectiveness. No one can bring Voyager into a laboratory and inspect every component. Everything humanity knows must be inferred from temperature and voltage sensors, along with the way each system responds after receiving a command. Shutting down a system aboard Voyager is very different from unplugging a device in a warm room. On Earth, the equipment could be turned on again after several months, cleaned, or repaired with a replacement part. In space, inactive hardware may spend years growing colder without maintenance. By the time engineers need it again, it may no longer respond, even if electricity is theoretically restored. Some instruments have returned to operation after being dormant for long periods. But every attempt carries risk. Engineers must consider the current temperature, the amount of power required, and whether old software can still control the system correctly. Switching on an instrument can also create a sudden electrical demand that exceeds the remaining safety margin. No operation is truly small when the entire spacecraft has so little energy left to share. For decades, the Voyager team has lived with a constantly changing balance sheet. On one side are the remaining electricity, the temperature of each region, and the stability of the communications system. On the other are scientific measurements that no other spacecraft can make from the same location. Keeping everything active at once is no longer possible, so the mission has been extended through a long series of carefully calculated reductions. The radio transmitter is one of the systems that can hardly be sacrificed. No matter how valuable the data may be, it becomes meaningless if there is no way to send it home. By the time Voyager's signal reaches the antennas on Earth, it is so weak that enormous receivers and careful processing are required to distinguish it from the background noise. Reducing the transmission power too far could cause the spacecraft's reply to disappear into that noise. The computers and control systems must also remain stable. They not only carry out commands sent by people on Earth, but also monitor the safety limits within the spacecraft. If voltage, temperature, or orientation moves beyond an acceptable range, Voyager can respond automatically before Earth even knows something has happened. With nearly a full day of communication delay, that ability to protect itself is an essential part of the mission. Low voltage is one of the situations monitored most closely. When the power supply can no longer support the active electrical load, the system voltage may fall below a safe threshold. Voyager can then enter a pre-programmed protective state, preserving its most basic functions while shutting down other activities. This mechanism helps prevent more serious damage, but it can also create a condition that is extremely difficult to recover from at the spacecraft's present distance. If the protective mode is triggered, the scientific instruments may stop collecting data. The spacecraft may also change the way it transmits or wait for a new sequence of commands from Earth. Every recovery step must travel nearly 23 hours to reach Voyager, and the reply requires almost the same amount of time to return. A problem lasting only a few minutes aboard the spacecraft can therefore become several tense days for the mission team. That is why NASA usually switches off equipment before declining power becomes an uncontrollable crisis. The decision is made while the spacecraft is still stable enough to carry out the planned command sequence. Waiting until the voltage has already fallen too low would take away the engineer's ability to choose the order and timing in which systems are shut down. Deliberately sacrificing part of the science is still better than allowing the entire spacecraft to enter a protective state on its own. In early 2026, Voyager 1's safety margin became even smaller after an adjustment caused its power level to drop more than expected. The change did not silence the spacecraft immediately, but it forced the mission team to shorten the time available for consideration. One scientific instrument had to be selected for shutdown to reduce the electrical load. After evaluating the power demands and scientific value of each system, the decision fell on LECP. On the 17th of April 2026, the command to shut down the instrument was carried out aboard Voyager 1. LECP had monitored charged particles from the days when the spacecraft was flying past the giant planets to the time it moved beyond the heliosphere. After nearly 49 years, its stream of data came to an end. The power it released gave Voyager 1 a little more safety margin to preserve the functions that remained. After this decision, Voyager 1 had only 2 scientific instruments still operating. Voyager 2, whose energy condition was slightly better at the time the article was published, continued to support 3. The 2 spacecraft were nearly identical when they launched, but they have aged in ways that are not entirely the same. A system that has developed problems on Voyager 1 may still be functioning on Voyager 2, and the reverse may also be true. The fact that 2 or 3 instruments remain does not tell the full story of each spacecraft's condition. Every instrument has different power requirements, temperature needs, and scientific value. A sensor that uses very little electricity may be preserved longer, while a more demanding system may have to stop even when its data remains useful. The mission team must consider more than the number of instruments. It must determine which combination gives the mission the greatest chance of remaining stable. The 4 watts lost each year do not disappear on any single day. The available power declines continuously and so slowly that the change is almost impossible to notice over the course of a week. Across many months, however, the safety margin grows smaller until a configuration that was once secure is no longer sustainable. Every instrument shutdown only returns Voyager to a temporary balance before the decline continues. The extra year gained by turning off LECP is not a year in which the power system stops aging. During that time, the generators will continue to weaken, the converters will continue to deteriorate, and the remaining components will endure another year of cold and radiation. The decision only lengthens the path toward the limit. The final destination does not disappear, but Voyager gains more time to send data before reaching it. The balance between electricity and heat has always been especially fragile. Turning off a heater saves power, but it can allow nearby equipment to grow colder and increase the risk of losing function. Keeping the heater active protects the hardware, but takes electricity away from communications or science. There is no perfect choice, only configurations that carry less risk during a particular stage of the mission. Communications competes with science in much the same way. An instrument may collect extremely valuable data, but both its operation and the transmission of its measurements require electricity. If too many sensors remain active at once, the radio transmitter and computers have less safety margin. If too many are switched off, the spacecraft may still be able to speak with Earth, but it will have fewer new things to say. This balance makes it impossible to predict Voyager's remaining lifetime with an exact date. One instrument may continue working longer than expected, while another component may fail sooner. The spacecraft's survival depends on both a decline that can be calculated and malfunctions that no one can foresee. Every additional year is therefore partly the result of engineering and partly dependent on whether the aging hardware continues to respond. The people operating Voyager are not trying to preserve the spacecraft exactly as it was in 1977. A more realistic goal is to protect an increasingly reduced version of the mission, one still capable of communicating and maintaining a few important measurements. The cameras are gone, many heaters have stopped operating, and scientific instruments have fallen silent one by one. What remains is continually rearranged to fit an electrical budget that has never stopped shrinking. Shutting down another instrument may buy roughly one more year, but individual reductions cannot continue forever. Eventually, Voyager will need a different way of distributing power, rather than simply turning off one system after another. NASA therefore began considering a larger change, one that would affect many parts of the spacecraft almost at once. This was no longer about shutting down a single sense, but about reorganizing how the entire spacecraft uses the small amount of energy it still has left. The name of the plan sounds like an explosion powerful enough to shake space itself, but at Voyager's location, nothing will actually explode, and no flash of light will appear for a telescope to see. Big Bang is simply the name the engineering team uses for the moment when many systems aboard the spacecraft are instructed to change state almost simultaneously. Once the command arrives, Voyager must complete the entire process on its own, with no human hand nearby. For many years, power aboard Voyager was conserved through a series of individual steps. A heater was switched off, a scientific instrument stopped operating, and then the mission team waited for data to return before confirming that the spacecraft remained stable. This cautious approach allowed engineers to observe the consequences of each change before moving to the next. But the remaining power has now become too limited for every transition to continue unfolding as slowly as it once did. Every active component draws a certain amount of electricity. When one system is switched off and another option is brought online, the spacecraft must pass through a transition between the two configurations. During that brief period, total power consumption may be higher, or distributed differently, than it will be in the final state. A system with a generous reserve could move through this stage easily, but Voyager no longer has such a wide safety margin. The Big Bang plan is designed to reduce the amount of time the spacecraft must spend between two states. Instead of changing one component and then waiting several days for a full round of communication, a large command sequence will move many systems into a new configuration during a single operation. Equipment that consumes more electricity will be shut down, while more efficient alternatives will be brought online. If every step proceeds as planned, Voyager will move directly into a new stable state without remaining too long in the temporary configurations between them. The purpose of this plan is not to return the spacecraft to the early years of the mission. The cameras that were shut down will not suddenly open their eyes again, and instruments that have spent decades growing cold will not all return to operation. Voyager will remain a machine nearly half a century old, with fewer senses than before. The engineers are only searching for a way to help the surviving parts of the spacecraft use electricity more efficiently. The first priority is to keep the voltage safely away from dangerous levels. If the total power demand exceeds what the generators can provide, the voltage may fall and trigger the protective system. Voyager would then begin shutting down activities automatically according to rules programmed long ago. Such an automatic response might protect the hardware, but it would also take away the mission team's ability to choose which systems should remain active. Temperature is the next limit the new configuration must respect. Turning off additional heaters would conserve electricity, but the fuel lines and other critical components cannot be allowed to become dangerously cold. Engineers must understand how heat from the generators moves through the spacecraft, which areas can tolerate lower temperatures, and which locations must remain protected. A watt cannot be removed from one place if the result causes an essential system somewhere else to lose function. Communication with Earth must also be preserved in every possible plan. Voyager may continue measuring magnetic fields or plasma, but the data will have no value if the radio transmitter lacks enough power to send it home. The large antenna must remain correctly aligned. The computers must process the data packets, and the transmitter must produce a signal strong enough to be detected. A power-saving configuration, therefore, cannot simply shut down everything except a single scientific sensor. The science that remains will be protected within the limits of the available resources. Voyager occupies a position that no other spacecraft can quickly replace, so every new month of data still has special value. Yet the mission cannot preserve every instrument simply because each one remains useful. The engineering team must find a combination light enough for the spacecraft to survive, but still capable enough that maintaining communication continues to have meaning. Every choice within the plan has been calculated on Earth. Models estimate how much electricity each component consumes, how temperatures may change, and how the voltage will respond when several loads are switched at once. Technical documents from the 1970s are still used alongside data collected during nearly 50 years of operation. Even so, a model is only a simplified version of the real spacecraft traveling through interstellar space. There is no third Voyager operating under the same conditions that can be used for a trial run. A ground-based model can test how the software processes commands, but it cannot reproduce nearly half a century of radiation and deep cold like the actual spacecraft have endured. Laboratory components have not aged in exactly the same way, and the wiring aboard Voyager may have changed after millions of hours of operation. The final test must still take place on one of the two spacecraft themselves. The engineers have decades of experience to guide them, but that experience cannot remove every surprise. Voyager has often carried out operations exactly as expected, yet there have also been times when it responded differently from the original models. One aging component may continue working far beyond its design limits, while another may weaken in a way that is difficult to detect from Earth. Every decision contains some uncertainty that no calculation can completely erase. Voyager 2 was chosen for the first test because its energy condition was more favorable and it was closer to Earth than Voyager 1. That difference does not make the spacecraft completely safe, but it gives the mission team a little more reserve. Its signal also takes slightly less time to travel between the spacecraft and Earth. If something unusual appears, the engineers may have a little more time and information to understand the problem. Choosing Voyager 2 does not mean that it is less important than its twin. It is still returning unique measurements from a different direction in interstellar space. Any serious malfunction could erase a source of data that no other spacecraft can replace. Testing the plan on Voyager 2, therefore, remains a choice between two scientific assets that can never be recovered. Before the command is sent, every step must be reviewed again and again. The power team checks the electrical load of the new configuration. Thermal specialists examine the risks in the coldest regions, and the flight control team reviews the order of the instructions. The communication system must prepare for the expected time when the reply will return. A small error in the command sequence could travel tens of billions of kilometers before anyone realizes it exists. Once the command leaves the antenna on Earth, control temporarily passes to the spacecraft. The signal continues moving at the speed of light, yet still requires many hours to reach Voyager 2. During that wait, the mission team cannot add a forgotten step or correct an order that suddenly seems less than ideal. The instructions must already be complete from the moment they begin leaving the planet. Voyager receives the command sequence without knowing that humans consider it an important moment. The onboard computer simply reads each instruction, checks the required conditions, and carries out the program. Some systems stop drawing power, others move into new operating modes, and engineering sensors record the changes. The entire process unfolds in silence, with no outward sign that the spacecraft is being reorganized from within. Even after the operation is complete, Earth still does not know the result. Confirmation data must be gathered, transmitted through the large antenna, and sent back across the distance. Engineers can estimate when the signal should arrive, but impatience cannot shorten the space between them. For many hours, every prediction remains only a possibility on a screen until the antennas receive the spacecraft's actual reply. One of the risks is that a component may not enter the correct state. It could continue drawing power even after being told to shut down, or the prepared replacement may fail to activate. In that case, the total electrical load would differ from the model, and the remaining safety margin could be smaller than expected. The mission team would then have to identify the cause from limited numerical data before deciding how to respond. The amount of power saved may also differ slightly from the calculations. The equipment has aged, the efficiency of the power system has changed, and some real levels of consumption can only be known once the new configuration begins operating. A small discrepancy that would not have mattered during the early years may now become important. With so little reserve remaining, every watt that fails to appear as expected can force the entire plan to be reconsidered. The cold introduces another kind of uncertainty. A component that has remained at a low temperature for many years may respond slowly, draw an unusual amount of power, or fail to enter the requested state. Testing limits established in the 1970s did not cover every condition Voyager is experiencing today. The spacecraft has survived so far beyond its original mission that its age has become an environment of its own, one that was never fully tested. If the voltage falls too low during the transition, Voyager may automatically activate its protective mode. Some scientific operations would stop, the communications configuration could change, and the spacecraft would begin prioritizing its most basic functions. That system exists to prevent more serious consequences, but recovering from it remotely would require several additional rounds of commands. Each exchange would take tens of hours before the next step could be decided. Whenever something unusual happens, the human response always comes afterward. By the time engineers receive a signal showing that a problem has occurred, the situation aboard Voyager has already been unfolding for many hours. A corrective command prepared afterward then needs nearly another day to reach the spacecraft. Across this distance, direct control is really a sequence of actions and responses separated by very long periods of waiting. For that reason, Big Bang is not a reckless act born of desperation. Every risk is weighed against the consequences of making no change at all. If Voyager remains in its current configuration, the available power will continue to decline, and the voltage will move steadily closer to the danger threshold. Doing nothing is also a choice, and its outcome is one the engineering team can already foresee. The difference lies in accepting a calculated risk to avoid a certain decline. A new configuration may create more time, while the old one can only continue shrinking the remaining safety margin. No one wants to make simultaneous changes to an electrical system nearly 50 years old. But eventually, caution no longer means leaving everything exactly as it is. The name Big Bang makes the plan sound more dramatic than it will appear. Aboard Voyager, electronic switches will simply change state. Electrical power will be redistributed, and certain systems will move into more efficient modes. There will be no moment when the spacecraft is revived, in the sense of returning to its original condition. If the plan succeeds, it will only allow a very old machine to perform fewer tasks for a longer time. The plan announced in the spring of 2026 called for testing the changes on Voyager 2 during May and June. If the data showed that the new configuration was stable, Voyager 1 could receive a similar plan as early as July. This sequence would allow engineers to learn from the spacecraft with the larger power margin before sending commands to Voyager 1. However, the two spacecraft have aged differently, so success on one would not automatically guarantee an identical result on the other. Voyager 1 carries its own history of malfunctions and system configurations. Some instruments were shut down at different times. Temperatures in different regions do not exactly match those aboard Voyager 2, and its electrical reserve is smaller. The command sequence for the more distant spacecraft must therefore be adjusted to reflect its actual condition. Big Bang is not a single identical button pressed for both Voyagers. If the test produces good results, the electricity saved may allow Voyager to maintain communications and scientific operations for longer. An instrument that is currently inactive might even be reconsidered if the power budget permits, but every possibility must remain secondary to the stability of the spacecraft. The main objective is still to prevent an unexpected power shortage and preserve the essential functions. Any additional benefit can come only after the new configuration has proved safe. The result may also be more modest than hoped. Voyager may save less power than calculated, forcing the mission team to shut down more equipment in the near future. Some components may perform well, while temperatures elsewhere begin falling too quickly. The success of the plan will not be measured only by whether the spacecraft replies after the operation, but by whether it can sustain the new state for many weeks and months. No single signal will therefore be enough to declare that every danger has passed. The first reply will confirm only that Voyager is still communicating and that its main systems have not suffered an obvious failure. Later data will reveal whether the voltage remains stable, how temperatures are changing, and whether the scientific instruments are still operating correctly. The gamble can be properly judged only after the spacecraft has lived with the new configuration for long enough. Even in the best possible outcome, Big Bang will not create a new source of energy. The plutonium will continue to decay, the converters will continue to age, and the available electricity will keep declining year after year. The plan will only arrange the remaining energy more efficiently, like extending a limited reserve by using it more slowly. The clock will not stop, but its hands may move forward at a gentler pace. Every month preserved will give Voyager more time to measure the interstellar environment. Every additional year will carry the spacecraft farther and add another section to an observational record unlike any other. In return, the mission must survive in an increasingly minimal state, with very few instruments still permitted to operate. Voyager's continued existence is gradually being measured by what it can still preserve after so many capabilities have had to be surrendered. On Earth, engineers continue preparing every step with the caution of people who know there will be no opportunity for direct repair. On the far side of a distance approaching one light day, Voyager simply waits for its next command, unaware of the meaning humans attach to it. Between the two lies an expanse of darkness too vast for any rapid assistance to cross. Every hope must be packaged into precise lines of instructions before beginning the journey. Even if the new configuration works perfectly, it cannot stop the power supply from continuing to decline. Big Bang can only change the way Voyager approaches its limit. It cannot remove that limit. A few additional years of data would still be a remarkable success. But somewhere ahead remains a day when the spacecraft will no longer have enough energy to answer. When that day arrives, the final signal may disappear without carrying any farewell. Voyager's final signal may not sound like a farewell. It may be nothing more than an ordinary stream of data containing temperatures, voltages, and small measurements from interstellar space. No one receiving it may know for certain that it is the last time the spacecraft will answer. Only during the next listening session, when nothing clear enough to understand appears on the screen, will the silence begin to carry a different meaning. The Voyager mission may end in several layers rather than stopping in a single moment. The scientific mission may close first, when there is no longer enough power to keep any observing instrument active. Even then, the spacecraft may still return engineering data describing temperatures, voltages, or the condition of its internal systems. Voyager would still be speaking with Earth, but it would have fewer new things to tell us about the space through which it is traveling. Later, the remaining energy may be enough only for the most basic functions. The computers may continue operating. The control system may still try to keep the antenna pointed correctly, and the radio transmitter may send increasingly simple signal. Scientific data could disappear entirely, while engineering information becomes less frequent or is transmitted at a lower rate. At that stage, the mission would no longer be exploration in its original sense. but an effort to confirm that the spacecraft has not yet stopped responding. Another stage would begin when maintaining orientation becomes increasingly difficult. Voyager uses tiny amounts of propellant to rotate its body and keep the large antenna pointed toward the narrow region of sky where Earth is moving. If the fuel lines become too cold, the thrusters weaken, or the orientation sensors lose stability, the antenna may drift away from the required direction. The spacecraft may still exist, but its signal would no longer be aimed toward the receiving stations waiting on Earth. Transmission power creates a separate limit. Radio waves leaving Voyager spread outward as they travel through space, distributing their energy across an ever larger area. By the time the signal reaches Earth, it is only an extraordinarily faint trace hidden among many natural and human-made sources of noise. If the spacecraft's available power falls further, the transmitter may continue operating, while its voice becomes too weak to distinguish clearly. Losing contact would therefore not necessarily mean that every circuit aboard Voyager had stopped working. The spacecraft might continue performing some operations, generating data, or transmitting for a short time after Earth could no longer hear it. The difference would be that there was no longer a path for that information to cross the distance and be recognized. From that moment onward, the true condition inside Voyager would become something humanity could no longer confirm. On Earth, the task of listening belongs to NASA's Deep Space Network. Its 3 antenna complexes are located in California, near Madrid, and near Canberra, spaced roughly 1/3 of the way around the planet from one another. As Earth rotates and one site gradually loses sight of the spacecraft, another can continue following it. This arrangement allows interplanetary missions to remain in contact for longer periods. The enormous antennas do not simply point toward the sky and wait for a sound to arrive. They must know exactly where Voyager will appear, what frequency its signal should have, and how the relative motion between the spacecraft and Earth will shift that frequency. Sensitive receivers search for a very specific pattern within a broad field of noise. Only then can processing systems attempt to reconstruct the bits of data Voyager encoded long before the signal finally arrive. Listening time is also a limited resource. The Deep Space Network serves not only Voyager, but many spacecraft operating around Mars, the Moon, and elsewhere in the solar system. Antenna schedules must be arranged, so each mission has enough time to receive commands and return data. For a signal as weak as Voyager's, listening for longer periods, or combining the capabilities of several antennas, can sometimes improve the chances of recovering clear information. Every packet of data reaching Earth left Voyager nearly a day earlier. What appears on the screen does not describe the spacecraft's present condition, but its condition at the moment the signal began its journey. If the data reveals a problem, that problem has already existed for many hours before engineers become aware of it. The human response always comes afterward, sometimes nearly 2 days later, when both the outgoing repair command and the returning reply are taken into account. That distance is still increasing. Voyager 1 is not standing still while Earth slowly catches up. It is moving away from the Sun by hundreds of millions of kilometers each year. NASA has said the spacecraft is approaching the milestone of 1 light day in one-way signal travel time. Every future exchange will therefore be slightly slower than the one before it. A light day is not a wall that changes a signal once it is crossed. It is simply a milestone that helps us understand how vast the distance has become. When Voyager was launched, commands required relatively little time to reach the spacecraft during the early stages of the journey. Nearly half a century later, a question sent today may not receive an answer until the day after tomorrow. If Voyager remains silent during one listening session, the mission team will not immediately conclude that the mission has ended. First, they must check whether the receiving station is operating correctly, whether weather has affected the signal, and whether the observation used the expected frequency. Antenna pointing, processing systems, and data from the ground equipment are all reviewed. Sometimes an empty screen begins with a problem on Earth rather than aboard the spacecraft. After ground-based errors have been ruled out, engineers may search across a wider range of frequencies. Temperature or changes in Voyager's electrical system could shift the transmission away from its expected value. An extremely weak signal may still be present, but located outside the region where the receiver initially focused. Expanding the search helps determine whether the spacecraft is truly silent or simply speaking in a slightly different voice. A callback command may also be sent. Voyager could be instructed to enter a prepared communications state, use another transmitter, or perform a maneuver that helps point the antenna back toward Earth. Once the command leaves the planet, no one knows whether it reaches the spacecraft or whether the onboard computer processes it successfully. The entire team must wait through both the outward and return journeys before deciding what to do next. A single unsuccessful attempt would not be enough to close nearly 50 years of operation. Several different command sequences could be prepared, each based on a different explanation of what might be happening inside the spacecraft. Long waiting periods would separate each attempt, causing the search to continue for days or even weeks. During that time, the boundary between a temporary malfunction and a permanent ending would remain uncertain. Voyager has gone through periods when its data was interrupted or became difficult to understand, only to return to operation later. That experience makes the mission team cautious about reaching any final conclusion, yet the spacecraft's age and declining power mean that each new silence carries more serious possibilities than the one before. A method that restored Voyager in the past may no longer work now that its temperatures and available power have changed. There is no date already marked on a calendar for the moment Voyager will stop operating. Its electrical power declines at a relatively predictable rate, but the condition of each individual component cannot be forecast month by month. One part may continue working far beyond its design limits, while a connection or another device may fail without warning. The final moment will depend on a combination of measurable aging and failures that cannot be foreseen. NASA believes engineering data may continue to reach Earth for several years after scientific operations can no longer be sustained. In terms of receiving capability, the two Voyager spacecraft may remain within range of the Deep Space Network until around 2036, depending on whether enough power remains for the transmitters and on the actual condition of the spacecraft. This is not a guarantee that communication will continue until that year. It is only an estimated limit on how long Earth may still be able to listen, provided Voyager remains strong enough to transmit. Scientific operations may therefore end much earlier than communication itself. The final sensors may be switched off to protect the computers and radio transmitter, leaving Voyager unable to measure particles or magnetic fields. Afterward, the spacecraft may continue sending numbers that reveal how warm it remains and how its power supply is declining. A mission of exploration will gradually become a record of the health of the machine that carried out that exploration. When the engineering data also stops, Earth will lose the ability to know what happens next. Voyager may have run so low on power that the transmitter has shut down, but the antenna may simply have drifted away from Earth. A computer failure, a frozen fuel line, or a problem with the attitude control system could all produce the same result from the ground. The silence will offer no explanation for its own cause. In the days that follow, antennas may continue pointing toward the spacecraft's predicted location. Receivers may search for a weaker signal. New commands may be sent, and earlier data may be reviewed for warning signs that were missed. Each unanswered attempt will make recovery less likely, but it will be difficult to identify the precise moment when hope has ended. The mission may be declared over only after a process lasting far longer than the failure that first caused the silence. No one knows which packet of data will be the last. It may contain an ordinary magnetic field measurement, a sequence of temperatures, or only a few familiar engineering values. Voyager has no reason to create a special message because it cannot know which transmission will have no successor. The meaning of the final signal will emerge only later, in the minds of those who waited but received no new reply. That ending does not need to become a tragic scene. Voyager has operated many times longer than its original planetary mission and has crossed limits no earlier machine ever reached. A day of silence will not erase the data it collected or the planets it revealed from close range. It will only close the part of the journey that humanity was still able to follow direct. Inside the spacecraft, the power supply will continue to decline even after communication has ended. The computers may shut down, the heaters will stop operating, and the temperature of the components will gradually approach that of the surrounding environment. No one will arrive to remove the failed parts or confirm the moment when the final circuit stops carrying current. Voyager will change from an operating spacecraft into a human-made object, drifting along a trajectory shaped many decades earlier. That motion requires neither computers nor a radio transmitter to continue. In space, where there is almost no resistance, Voyager will keep traveling even after every system inside has fallen silent. It will not return to Earth, nor will it stop at some boundary after the mission ends. It will simply move farther away, carrying with it a small amount of material made on our planet. When the signal disappears, what truly ends is humanity's ability to know exactly what Voyager is experiencing. The radio thread that connected the two sides for nearly half a century will be broken, but the object at the far end will continue its journey. Attached to the spacecraft is a message, designed for a span of time far longer than the lifetime of its computers and power supply. That small object will carry Voyager's story into a future where no mission control station remains to guide it. Voyager's power may fade within the next few years, or perhaps the next few decades, depending on how much energy remains and how its aging components continue to endure the cold. But the spacecraft's motion does not depend on whether its computers are still running or its radio transmitter remains active. When Earth can no longer hear another reply, Voyager will continue moving away along a trajectory established long ago. The silence will end the mission, but not the journey. On Earth, every vehicle must constantly overcome resistance. A car burns fuel to work against friction with the road, while a ship must push water aside to move forward. Voyager, however, travels through an environment where almost nothing is dense enough to slow it significantly. After the rocket carried it away from Earth and the giant planets altered its velocity, the spacecraft no longer needed to burn its engines continuously to keep traveling. Voyager's small thrusters are used mainly to adjust its orientation, not to propel it across billions of kilometers. They help keep the antenna dish pointed toward Earth and maintain the instruments in the positions they require. When there is no longer enough power or attitude control fuel, that ability to orient the spacecraft will eventually disappear. Voyager may begin to rotate slowly, but its entire body will continue moving forward. The temperature inside will fall as the heaters gradually stop operating. The computers may shut down, the onboard clocks may lose their rhythm, and the final electrical circuits will slowly become inactive. By then, the antenna will no longer point precisely toward the region where Earth is moving, causing even a faint signal to miss the receiving stations. The material that makes up Voyager will remain long after every function that once made it an operating spacecraft has disappeared. The lifetime of the mission is therefore different from the physical lifetime of the spacecraft. The mission continues as long as Voyager can observe, process data, and communicate with the people waiting on Earth. The spacecraft itself may drift through space for far longer, even when no one can know the condition of the individual components inside. From a scientific instrument, Voyager will gradually become a human-made object carrying traces of the world that created it. Attached to each Voyager is an object designed with that silent future in mind. It is a gold-plated copper record about 30 centimeters in diameter, enclosed within a protective cover. When every transmitter has gone dark, the record will need no electricity to continue traveling with the spacecraft. It does not broadcast a signal or speak a greeting on its own. It simply rests on Voyager's body as a very small archive of Earth. The people who prepared the golden record did not attempt to preserve the entire history of humanity. No object so small could contain every culture, story, achievement, or conflict that has existed on our planet. They selected only a collection of sounds, images, and greetings, intended to offer a few impressions of the world Voyager had left behind. The result was not a complete portrait, but a brief introduction sent into an unknown future. The record contains greetings in many human languages. Different voices share a simple message. On a small planet orbiting the sun, there once lived beings capable of communication who wished to be recognized. Not every language on Earth is included, and each greeting lasts only a short time. Even so, the diversity of voices reflects a desire to present humanity as a community broader than any individual nation. The record also preserves the sounds of the ocean, wind, thunder, birds, and many other living creatures. There are footsteps, a heartbeat, and familiar signs of life on a planet with an atmosphere and oceans. These sounds do not explain how Earth works, but they carry the rhythms of a world shaped by water, weather, and living things. Even if no one beyond humanity ever hears them, their value remains unchanged. The music on the Golden Record comes from many periods and cultures. The selections could never fully represent every tradition, but they show that humans learned to shape sound into structure, emotion, and memory. Music was placed aboard the spacecraft because it is one of the things most difficult to express through images or numbers alone. A civilization that sent music into space left evidence that it once listened to the world and created sounds that reached beyond the simple needs of survival. The images encoded on the record depict people, animals, plants, landscapes, and several aspects of everyday life. They show the human body, families, food, tools, and Earth's natural environment. Some illustrations also introduce ideas of size, time, and the basic structure of matter. Those who prepared them understood that there was no guarantee the information would be interpreted correctly, but they still tried to create a starting point based on shared physical laws. Symbols engraved on the protective cover explain how the record's contents can be played. The diagrams also indicate the location of the sun by relating it to a group of rapidly rotating neutron stars in the galaxy. Rather than relying on the language of any nation, the instructions are based on time, frequency, and astronomical position. It was an attempt to turn a human-made object into a message that might be understood without any prior knowledge of a language spoken on Earth. All of this often leads to the question of whether extraterrestrial beings might one day discover the Golden Record. That possibility is not central to Voyager's journey, because the space between the stars is so vast that it is difficult to describe in familiar distances. Neither spacecraft is heading toward a known inhabited planet, nor were they sent along a course intended to encounter a particular civilization. They simply continue along their natural trajectories, while any meeting with another object in the distant future remains extraordinarily unlikely. The deepest value of the Golden Record therefore lies with the people who sent it. The object forced humanity to ask what it would want to be remembered for, when there was room to choose only a few things. Amid the wars, divisions, and unstable periods of human history, the message placed aboard Voyager focused instead on life, music, language, and the desire to communicate. It does not prove that humanity has always lived according to those values, but it shows that we once understood what we hoped to become. A message does not need a recipient in order to have meaning. Creating it was already a way for humanity to look back at itself from the imagined distance of the universe. Differences that once seemed enormous on the ground became smaller when the entire planet was placed onto a single record. The Golden Record does not erase human conflict, but it reminds us that all those languages, songs, and memories began on the same world. Voyager 1 and Voyager 2 will not pass near another star anytime soon. More than 38,000 years from now, Voyager 1 is expected to pass the star, commonly known as AC plus 793888, at a distance of about 1.7 light-years. Even that distance is thousands of times greater than the journey from Earth to the outer region of the planets. It will only be a very distant passage, not a visit to another star system in the ordinary sense. Voyager 2 will continue along the separate path created by its flyby of Neptune. In about 40,000 years, it will pass roughly 1.7 light-years from the star Ross 248. That star was not chosen as a destination, and Voyager has no ability to change course and move closer. Its trajectory will simply carry it through a region that is relatively near the star when measured on a galactic scale. Tens of thousands of years is longer than the entire history of modern cities. No one knows what Earth will be like by then, which cultures will still exist, or whether humanity will continue to remember Voyager. The two spacecraft will follow their trajectories regardless of how names, languages, and borders on our planet may change. Their time is no longer measured in political terms, generations, or individual lives. Even so, we should not assume that Voyager will remain perfectly intact forever. Collisions with dust particles, radiation, and the gradual aging of materials will continue to affect the spacecraft. Over immense spans of time, their surfaces may be altered, and their components may deteriorate in ways that are difficult to predict. They may outlast the technology that created them, but they are not immortal objects. Returning to 2026, that future of tens of thousands of years stands in sharp contrast to the decisions being made on Earth each day. Engineers are not steering Voyager toward a distant star. They are trying to keep its voltage stable and protect the last few operating instruments. A single watt of electricity, one heater, or one command sequence may determine how much longer the spacecraft can continue returning data. While its future trajectory stretches across millennia, the remaining active mission is measured in years, months, and sometimes individual communications. The two Voyagers began their journeys by viewing planets from close range that humanity had previously observed only from far away. Their cameras recorded storms, rings, moons, and surfaces that had never appeared clearly in any image before. When the era of photography ended, the spacecraft continued with instruments that measured particles, plasma, and magnetic fields. The journey did not stop when Voyager could no longer see. It simply shifted to a quieter form of observation. Later, both spacecraft crossed beyond the region dominated by the solar wind and entered the interstellar environment. No gateway opened before them. There were only gradual changes in the data. Particles from inside the heliosphere declined, cosmic rays from the galaxy increased, and plasma density revealed that the spacecraft had entered a new region. Because of Voyager, the outer edge of the sun's influence changed from an idea in a model into a place touched by human-made instruments. Today, the mission is no longer about carrying Voyager to another planet. The spacecraft's trajectories have already been shaped, and no nearby destination is waiting ahead. The work on Earth is now simply to keep the few remaining senses operating for a little longer. Every new measurement is a reward from a machine that has survived far beyond its original assignment. What Voyager leaves behind is not simply the achievement of traveling farther than anything else. Distance matters, because the spacecraft has continued sending information from that location back to Earth. It transformed a region of space that had never been measured directly into data humanity could study. Its greatest accomplishment was not merely traveling far away, but extending the reach of human curiosity. The journey also shows that exploration does not always require a spectacular moment. Many years of Voyager's mission passed without a new planet, a famous photograph, or an announcement that captured the world's attention. The spacecraft simply continued measuring subtle changes, while engineers quietly conserved every fraction of power. Science sometimes advances through the patience to maintain a measurement long enough for slow patterns to begin revealing themselves. The message Voyager offers is therefore not a celebration of an immortal machine. Nothing aboard the spacecraft is protected from decay, and no technical solution can keep it operating forever. Its value lies in the way humanity used a finite amount of time to look farther, listen more carefully, and continue asking questions after the original mission had ended. Limits do not make the effort meaningless. They are what make every remaining year of data so valuable. The golden record carries a similar meaning. It offers no guarantee that the story of Earth will ever become known to another civilization. But the decision to send greetings, music, and the sounds of life reveals that humanity did not only wish to conquer the space ahead, we also wanted to be understood, to connect, and to leave some sign that within that immensity, there once existed a world capable of listening. On Earth, a great antenna continues pointing toward the region of sky where Voyager is traveling. Nearly 1 light day away, the small spacecraft transmits a signal so faint that it almost dissolves into the noise of the universe. No physical thread connects the two places, only radio waves crossing the darkness and people patiently waiting for them to return. Each time the signal is detected, that immense distance is briefly bridged again. One day, the antennas will point toward the correct location but find no reply. Commands may be sent several more times, while the receivers listen longer before the silence is accepted. No one knows on what day the final packet of data will arrive or what it will contain. But when the signal stops, Voyager will not disappear from space. The spacecraft will continue along the trajectory given to it by planetary encounters that occurred decades ago. The golden record will remain attached to its body, carrying greetings, ocean waves, music, and images chosen from a world now far behind. There will be no operator, no guiding signal, and no predetermined destination. Only motion continuing through a region of the galaxy wider than any journey humanity has ever directly undertaken. Voyager will not carry humans to the stars, but for nearly half a century, it has pushed the boundary of where humanity can see, measure, and listen farther than any machine before it. Its journey reminds us that curiosity does not have to defeat time in order to matter. It only needs to travel a little farther than the limits reached by the generation before. Even after the final signal has faded into the darkness, the two spacecraft will continue carrying traces of Earth, quietly moving deeper into the galaxy we call home.